Salam Sejahtera and very good day to everyone. My name is Ringgau from the Department of Electrical Engineering, Politeknik Mukah. Today I will present our research title, A Small-Scale, LoRa-Based Environmental Monitoring System for Phytophthora Capsici Mitigation in Sarawak. This research focused on developing a low-cost monitoring system to help pepper farmer monitoring soil condition and prevent crop disease using LoRa communication technology. Sarawak is one of the leading producer and exporter of high-quality black pepper, scientifically known as pepper nigrum. The major challenge faced by pepper farmer in Sarawak is the high risk of Phytophthora Capsici infection. This disease thrives in humid, warm, and rainy environment, especially in acidic and waterlogged soil. Studies show that approximately 46.3% of pepper crops in areas such as Sibu, Sarike, and Bintulu are affected by this pathogen. Another challenge is that many pepper farmers are located in remote rural areas where internet access is limited. Because of this, farmers cannot easily monitor environmental conditions or receive timely technical report. Therefore, continual monitoring of soil, moisture, temperature, humidity, rainfall, and pH is essential to reduce the risk of disease outbreak. The objectives of this project are: first, to develop a real-time environmental monitoring system that can measure important parameters affecting pepper cultivation. Second, to implement LoRa communication technology for a long-range wireless data transmission without relying on internet infrastructure. And third, to develop a user-friendly interface that allows farmers to monitor environmental conditions and system status easily. This slide shows the block diagram of the system architecture. The system consists of two components, the transmitter module and the receiver module. The transmitter collects data from several sensors, including soil moisture, pH, temperature, humidity, and rain sensor. These sensors are connected in Arduino Mega 2560 microcontroller, which processes the sensor signal, and the data is then transmitted using LoRa communication module to the receiver. The receiver sends the data to the computer where it is displayed on monitoring dashboard. The system also controls irrigation and drainage pumps through relays. Pilot pump indicate when irrigation or drainage is activated. In the methodology stage, we first designed the sensor node system. Several environmental sensors were installed at different depths in the soil to obtain accurate readings from the root zone of the pepper plants. For example, the soil sensor was placed at 15 to 13 centimeters depth. pH sensor was placed at 10 to 15 centimeter depth. Other sensors include temperature and humidity sensors using DHT11 module as well as rainfall sensor. All sensors are connected to the Arduino Mega 2560 microcontroller, which processes and prepares the data for transmission. For communication, we use LoRa modules operate at 915 MHz. LoRa technology is well known for its long-range, low-power wireless communication capability. Under ideal rural conditions, LoRa communication can reach distance up to 63 kilometers. This makes LoRa highly suitable for remote agriculture monitoring, where internet infrastructure may not be available. The system also uses a real-time clock module to record the exact time for every measurement. The system also includes an automatic irrigation mechanism. When the sensor detects high temperature, low humidity, low rainfall, and low soil moisture, The Arduino activates the diaphragm pump through a relay. The pump supplies water through a misting nozzles, which distribute a fine spray to water across the pepper plants. This helps maintain suitable soil moisture and reduces plant stress during dry conditions. Once the environmental condition returns to normal level, the system automatically turns off the pump to conserve water. In addition to irrigation, the system also includes an underground drainage system. This drainage system prevents waterlogging, which can damage plant roots and promote fungal growth. The tight drainage system consists of gravel layer for water flow, perforated PVC pipe, geofabric sheeting to support filtration and prevent soil from clogging the drainage system, and a submersible pump. When the soil moisture becomes too high, the Arduino activates the drainage pump to remove excess water. An orange pilot lamp indicates that the drainage process is activated. The system programming begins with initialization, where the Arduino activates the sensor, LoRa modules, and RTC modules. The system then continuously reads sensor data, including soil moisture, rainfall, pH, temperature, and humidity. Next, the program compares the measured value with predefined threshold condition. For example, irrigation is triggered when temperature exceeds 30 degrees Celsius, humidity is 70% or lower, and rainfall is less than 7 mm. Drainage is activated when soil moisture exceeds 80%. The process data is then transmitted via LoRa to the receiver and displayed on the monitoring dashboard. The calibration results showed that the sensors perform consistently. For example, the rain sensor showed a linear relation between voltage and rainfall detection. The soil moisture sensor demonstrates stable readings between 0 and 1023 digits value. The pH sensor successfully classified soil condition into acidic, neutral, and alkali zones. These results confirm that the system can effectively monitor environmental conditions in pepper plantation. The LoRa communication test evaluated the relationship between distance and RSSI, which indicate signal strength. The results show a negative relationship where signal strength decreases as distance increases. However, even at distance of 10 kilometers, the signal strength remained around negative 45 dBm, which is still reliable for a rural communication. This demonstrates that LoRa provides stable and predictable long-range connectivity. A 3-day field simulation test was conducted from 18 November to 20 November 2024. During the test, soil moisture ranged between 40 and 52%. Soil pH remained stable between 5.4 and 5.6. Daytime temperature ranged from 28 to 30 degrees Celsius, while nighttime temperature were 24 to 25 degrees Celsius. Humidity levels were high at night, which is consistent with typical tropical environment condition. These results confirm that the system successfully captured environmental change and supported automated irrigation and drainage decisions. The interface provides real-time monitoring, CSV data logging, and conditional alerts for soil and environment parameters. The dashboard displays several important parameters including date, time, soil moisture, soil pH, temperature, humidity, and rainfall. It also includes status level that indicate whether the system is operating under normal condition, irrigation mode, or drainage mode. In addition, the interface provides several functional buttons that allow users to view image, check the system location and download recorded data in CSV format for future analysis. The software continuously receive data from the LoRa receiver, update the monitoring table in real time, and automatically store the readings for future analysis. During testing, when all environmental parameters were within the exception range, the system display condition normal. At this stage, both the irrigation and drainage pilot lamp remained off, confirming that no correction action was required. This is the dashboard interface during automated water management operation. When the system detects high temperature above 30 degrees Celsius, humidity at or below 70%, and rainfall below 7 millimeters, the system identifies dry environmental condition. As a result, the dashboard updates the status to water pump into field, indicating that the irrigation system had been automatically activated. On the other hand, when the soil moisture exceeds the optimal threshold due to heavy rainfall, the system activated the drainage pump to remove excess water. The dashboard then updates the status to water pump out of field, informing the user that the drainage system was operating. This automated response helps maintain optimal soil condition for pepper plants and reduce the risk of disease caused by excessive soil moisture. The estimated component cost of the system is approximately around RM 1050, considering manufacturing, software development, maintenance costs, and estimated market price would range between RM 2625 and RM 3150 per unit. Each unit can cover approximately 0.18 to 0.20 hectare of farmland. With appropriate maintenance, the expected product lifespan is between 5 to 8 years. This makes the system a core effective solution for a smallholder for pepper farm. The impact of this system is significant. First, it reduces the time and effort required for farmers to manually check soil conditions. Second, it helps prevent crop losses caused by Phytophthora Capsici infection. Third, the system promotes sustainable water management by preventing both over-irrigation and waterlogging. Ultimately, this technology can help improve productivity and profitability for pepper farmers in Sarawak. In conclusion, this project successfully developed a portable, cost-effective, and energy-efficient soil monitoring system. The system operates without internet connectivity, making it suitable for remote agriculture areas. Initial testing demonstrates that the prototype functions reliably and can monitor environmental conditions accurately. With further long-term testing and improvement, the system has a strong potential to support sustainable pepper farming and disease prevention in Sarawak. In conclusion, this project successfully developed a portable, cost-effective, and energy-efficient soil monitoring system. The system operates without internet connectivity, making it suitable for remote agriculture areas. Initial testing demonstrates that the prototype functions reliably and can monitor environmental conditions accurately. With further long-term testing and improvement, the system has a strong potential to support sustainable pepper farming and disease prevention in Sarawak.